Okay, yeah. So, hello everybody. I am Krishiv Khandewal, and today's topic is cryptography. So, yeah. So, basically, what is cryptography? Could anyone give any sort of ideas as to what cryptography could be? Also, please try to reply if you can, I guess. Mm, no one? Okay, sure. So, cryptography is basically the method of concealing and revealing, or more formally, encrypting or decrypting any sort of text, but they're usually messages of some sort. So, whenever we send messages in this session, I'll always talk about the messages as being sent from Alice to Bob or A to B. Okay, so a cipher is basically an encryption algorithm, basically a method of concealing text. So we'll start by looking at a simple cipher called the Caesar cipher. So, okay, so let's imagine Julius Caesar on the battlefield and he sends this message to someone. Now, this is probably not actually some actually readable, right? Unless it's in some obscure language. So we'll understand that it's in some sort of code. And you might have done this in school or somewhere, but so this is basically we shift every single letter back 5 times. So F goes to A, G goes to B, and so on. So like this message gets sent to need salad by Caesar, which is fine, but what if there is a letter like A in the cipher text or the encrypted text? What do we do then? So basically, then what we'll do is we'll cycle back to Z. So we'll go A, Z, Y, X, W, V. So A goes to V. And already, since we're cycling back, we are starting to see some sort of modular arithmetic in play here, which is basically like the encrypted letter is the non-encrypted letter or the plain text plus some key modulo 26, and here the key is -5 because we're going back 5 times. So this is basically something we call a shift cipher because we're shifting everything, right? So, right. So the thing is, we don't really need to limit ourselves to only shifting the letters. We can also produce any sort of permutation of the alphabet, such as A going to C and B going to H and C going to A, right? So that also works. And our substitution ciphers basically become a bijection from F in the set A, B, C, D to Z to the set A, B, C, D to Z. So there are 26 factorial of these substitution ciphers, since there are 26 places for A to go to, 25 places for B to go to, and so on. So it should be very hard, if not impossible, to break any of them if we pick a code at random. But that's actually not true. So why is it not true? It's not true because, so let's say we have some sort of cipher text, and let's say this text, right? Let's say there is this text. And here, note that the letter Z and the letter V appear a lot of times. Z appears 1, 2, 2, 3 times, and V appears 1, 2, 3, 4 times. So obviously we can note that letters that are actually repeated more times in the actual English language will correspond to the letters that repeat more in the ciphertext. So statistically, E is the letter that is repeated the most, and other letters like A, T, S are after that. So here we can see that Z corresponds to E and V corresponds to A, which actually makes sense, but it starts to make more sense if we have a large sample of ciphertext. So yeah, that was substitution ciphers. Is everything clear up till this point?
Yes.
Nice. So we'll move on to a cipher which is called the Skytale cipher. It can also be spelled SCYTALE cipher. So what is this Skytale cipher? So basically, assume you have some text. Let us say we have a 27 letter string, and we know that it is encoded by the Skytale cipher. What do we do? What is the Skytale cipher? Basically, the Skytale cipher is just a cipher in which the letters are jumbled around, but they're jumbled around in a sophisticated way. So, like, you also might have done this in school. So, you might have sent messages, secret messages from one person to another by reversing the text. Like, suppose you have the word have. So, you actually send EVAH instead of HAVE. But the Skytel cipher is kind of like that in the sense that we are jumbling the letters around, but it is more sophisticated. So both of these ciphers are called transposition ciphers, and we can see why they're called transposition ciphers because we're changing the positions. So yeah, that's nice. But yeah, so what is the Skytel cipher? Basically, imagine the string of text. Like, imagine the plain text being wrapped around a cylinder, right? So, if you read it vertically, right? If you read it vertically, you'll read the plain text as it is. But suppose you read it horizontally instead of vertically. So, basically, you have this sort of cylinder, and you're writing H A V E and so on. So if you read it like this, vertically, then you'll read HAVE, have, which is pretty obvious. But if you read it horizontally, one second, yeah. So if you read it horizontally, you read AEHV or HAHVAE. So yeah, that is what the Skytel cipher is. We can, instead of interpreting this as a cylinder, we can interpret this as a grid of sorts. So an obvious thing one can note is that if we have, let's say, 45 letters, when we arrange them into a grid, it can form one of three grids. It can form a 1 into 45 grid, it can form a 3 into 15 grid, or it can form a 5 into 9 grid, right? I hope I'm not forgetting any cases. Yeah, so these are the ways we can do this. But we can also take 45 into 1. That is, if we arrange the letters horizontally, like this, and read it vertically, or if we arrange it vertically and then read them horizontally. So there are actually 6 ways. So the way one can decode this is if they know the key, that is 5 into 9, say. If they know 5 into 9, then they can just arrange it horizontally and read it vertically. But if they don't, if there is an attacker, say E, and E wants to find out what the message being sent is, then E can basically arrange it in all the possible ways, which is only 6 ways here, right? So this is actually quite easy to crack because there are only a finite number of ways that one can factorize numbers, and it's a small number, right? So there's that. So yeah, it's very easy to decode. We have an exercise, we have a problem over here, which we'll come back to at the end. So it's basically that Alice is encoding a message in the Skytel cipher. We do not know the key, and this is the text, this is the encrypted text, and we have to decode what it is. Right, so now we'll actually move on to some interesting ciphers and some interesting mathematics. So, right. So now, okay, wait, before we continue, does anyone have any doubts as of yet? Or any sort of questions? You can ask questions if you have any. I'll move on if I do not hear any questions. Okay, nice. So, right. So now, suppose Alice wants to send the confidential message power to the people to Bob. So now in this cipher that we're about to discuss, what Alice will do is she'll divide the letters into pairs like PO, WE, RT, so on until LE, and then she'll write them in an alphanumeric code, which basically means we're translating the letters to their numbers in the alphabet. So P is the 16th letter, O is the 15th letter, W is the 23rd letter, E is the 5th letter, and so on. So we basically converted the letters to numbers, which is why we know we can use mathematics to encode this. So, right. So the highest number that can be reached is 2626, which corresponds to ZZ. Right. So in this cipher, we'll choose a prime greater than 2626, let's say 2819. Uh, Rest assured, 2819 is actually a prime and I'm not lying. So yeah, so our, our exponentiation cipher will work like this. So the cipher text will be the plain text to the power of the key modulo 2819. Right, so okay, that's fine. So basically this whole string, so like 1615 to the power of the key modulo 2819 will be the cipher text for 1615. 2305 to the power of the key modulo 2819 will be the cipher text, and so on and so forth. So okay, that's nice. Why should this be any better than our previously discussed substitution and transposition ciphers? Because the other people apart from Alice and Bob, the other people or the attackers don't have the key. So right, so that's fine. We'll see what happens about that later. But now, how does Bob decrypt this message with the key? So what Bob can do is he can find a key bar such that ciphertext to the key bar is the plain text, and he'll be done, right? But by the first equation, this one, we know that the ciphertext is plain text to the power of key. So basically, this equation becomes plain text to the power of key bar into key. This is basically just the plain text modulo 2890. Right. Now, what does this imply? Does anyone want to say what this implies? this one. What does this imply, or should I say what it implies? Mm, no one? Okay. So this basically implies that key bar into key is 1 modulo 2818. Why? Because 2819 is a prime, and by Fermat's little theorem, we have that key bar into key should be 1 modulo p minus 1, which is in this case 2819 minus 1. So yeah, so key bar is basically an inverse to key modulo 2818. When does an inverse exist to key modulo 2818? When, when, anyone? No one? Yeah. So an inverse exists when the GCD of key and 2818 is 1. Okay. How can we find this using like Euclidean algorithm and other standard techniques? Okay. So yeah. So how does one attack this, as we were discussing before? So brute force shouldn't be a problem, and because we're picking a prime large enough and it will not make sense for someone to brute force it. But suppose the attacker has a sample set where they know both the plain text and the corresponding ciphertext for a few strings. Then what the attacker can do is they can guess a few possible values of the prime by looking at the largest number in the ciphertext. But there will still be some amount of brute forcing involved. But yeah, they can guess the prime, and now the attacker knows the value of the prime, and they can simply keep multiplying the plain text by itself, since we're exponentiating the plain text. So they can keep multiplying the plain text by itself until they get some meaningful ciphertext that they want. But now, if we say that this is a long process, then isn't that exactly what Alice does to encrypt? The answer is no. Alice doesn't actually use that long way to encrypt. What Alice does is Alice just works base 10. Basically, like if the key is 769, Alice goes plain text to the power of 10 to the power of 10 to the power of 7 into plain text to the power of 10 to the power of 6 into plain text to the 9, which is only 54 multiplications compared to the 768 multiplications the attacker has to do. So if our key is large enough, it will take much longer for the attacker to decrypt this. So now it is only natural that one asks, is there a better way for the attacker instead of keeping on multiplying and multiplying the plain text? So this is an open problem, and the problem is called the discrete logarithm problem. Why? Because we're basically taking the logarithm of the plain text modulo 2819. That's what we're doing. But we're not taking any straightforward logarithm here. What we're doing is we're working modulo 2819, which messes up things for the attacker, which is nice for us. So yeah, next what we will discuss is also a very interesting and very heard of thing, very heard of cipher. So this is called RSA. Most of you may have heard of this before. So there's a story behind RSA, and the story goes like this. So basically, there are three mathematicians slash computer scientists, Rivest, Shamir, and Adelman, who were given an opportunity to work on a cipher which was asymmetric. Basically, an asymmetric cipher means that the encryptor and the decryptor do not have equal amounts of information. So like everywhere else, uh, say say in this cipher, the the encoder, that is Alice, had the key, and Bob also had the key, and Bob computed a key inverse, right? So they basically had same amounts of information, but so these three mathematicians and computer scientists got an opportunity to work on an asymmetric cipher. So West and Shamir, R and S, were like, wow, this is a great opportunity for us. But Adelman was just like, meh, I'll just stick around to see what they do. I don't really care about this. So basically, what happened is Rivest and Shamir came up with more and more codes, and it is said that they had about 32 to 35 codes. And those first 32 to 35 codes, Adelman broke almost instantly, and the 33rd or the 36th code, whatever it was, Adelman took a whole night to break. And when it took Adelman a whole night to break that code, he was like, okay, this might actually be something fruitful. I will cooperate with Rivest and Shamir. And so RSA came to be. So what is RSA? So the what do you call it? The idea behind this is that there is no feasible algorithm to factorize a very, very large number in a polynomial or reasonable amount of time. So, okay, fair enough. How do we use this? So, what Bob does, or Alice, the name doesn't matter, but Bob, because Bob is the receiver here. So, what Bob will do is he will choose two primes, P and Q, which are very large, which are like 300 digits long. 300 digits long. And we know quite a few, like a lot of primes that are 300 or so digits long. Even more, we know very, very, very long primes. So it isn't a difficulty for Bob to find those primes. So he finds those primes, he multiplies them together, he gets this number called PQ. Nice. And what Bob does is Bob lets PQ be the encryption modulus, right? He lets PQ be the encryption modulus, and he basically uses this cipher. And he throws away P and Q. Throwing away P and Q is very, very important here. So basically, there's this plain text, right? There is this plain text, and so like there is some key, and he'll reveal the key to everyone, and he'll raise plain text to the power of e. Whoever the sender is will raise the plain text to the power of e, and they'll compute that mod pq. Okay, this p is the plain text, this p is the prime, don't get confused. So they'll raise plain text to the power of e, which is the key, which is public to everyone, modulo pq. And what, how will Bob decrypt this? Remember, Bob has to know the inverse of e modulo p, but in this case, since it's pq, we'll compute phi of pq, which is p minus 1 into q minus 1. And Bob can compute this because he has p and q and no one else does, right? So he'll compute phi of pq, he'll work out the inverse of e, which only he has, since no one else has phi of pq, and he'll raise the encrypted text to the power of that inverse, and he'll get the plain text. So basically, anyone can send Bob messages. Everyone has the key. Everyone has PQ. No one has PQ, P, Q, and the inverse. Everyone has PQ though. So yeah, since they don't have P and Q individually, they cannot attack this feasibly, which is a problem. So yeah, that's very, very nice. So how can one potentially attack RSA? So you can avoid all attacks to RSA if you are wise enough and if you do not blunder something. So this is another problem we'll come back to if we have time later on. Okay, now for the most interesting part of this session, which is elliptic curve cryptography. Before that, once again, if you have any doubts, please do ask. No doubts. Okay, nice. Moving on. Elliptic curve cryptography. You may or may not have heard of elliptic curves in some reference of maybe Fermat's last theorem, maybe not, but very unfortunately, we're not going to be discussing Fermat's last theorem today. Very, very sad. So, anyways, elliptic curve is an equation of the form y squared is equal to x cubed plus ax squared plus bx plus c. Okay, so it looks like one of them at least looks like this. This is an elliptic curve. We'll come back to what P, Q, and R and the line between them is right now. We'll come back to that, but yeah. So, why are these things interesting to us? Because what we can do is we can define an operation between 2 points, which we'll call addition on this elliptic curve. So, basically, given 2 points P and Q, what we'll do is okay, I'll have to find a more, yeah, this is better. So we have these 2 points P and Q, and we'll draw the line between them, and it intersects the elliptic curve at only one other point. So let's say this point is R. Don't actually read minus R, read it as R because that's what I've written. Haha. So R, and we'll reflect R about the x-axis, and note that the reflection actually lies on the elliptic curve. Why? Because elliptic curves are symmetric, basically, kind of about the x-axis. So yeah, the reflection lies on the elliptic curve, and we'll call that R dash. And that reflection we will define as P plus Q. Right, so P plus Q is R dash. Okay, nice. So, okay, what if we have only 1 point? What if we only have P? What if we only have Q? So if we only have Q, we'll define Q plus Q or P plus P equal to 2P in the same way. Basically, we have this elliptic curve and this is point P. We'll draw the tangent at that point. Okay, it will be better if I redraw this. So we have an elliptic curve and we have a tangent and the elliptic curve is like this maybe. So the point at which this intersects is yet again R dash. This is P. This will be R dash. Sorry, this will be R. And the reflection will be R dash, which we can also call 2P because it is P plus P. So the line PP we refer to as the tangent at P, which is kind of generally what we use. Right, nice. Color change. Hmm. So, okay, this is P plus P, this is P plus Q. What if we add R to R dash? R to R dash, if we add those two together, the line will go vertically upwards. And obviously, obviously since the elliptic curve goes forward, it won't actually intersect the elliptic curve at any other point. So this is very troubling. So we'll actually define a point called the point at infinity, which is basically where all of these vertical lines end up. So R plus R dash becomes, it goes to the point at infinity, and the reflection of the point at infinity about the x-axis is just the point at infinity. So we define R plus R dash or P plus P dash or Q plus Q dash to be the point at infinity. And if we want R plus the point at infinity, then basically R plus the point at infinity, the line intersects the elliptic curve at this point R dash, right? And the reflection of R dash about the x-axis is R. So r plus p infinity is r, p plus p infinity is p, q plus p infinity is q. So basically p infinity acts like an identity, since adding it to anything gives the same thing. And we have inverses. Basically p plus p dash is p infinity, which is the identity. So basically this establishes an abelian group. What is an abelian group? So first, what is a group? A group is basically a set with an operation. This is going into group theory a bit. So a group is a set with an operation where when we like use the operation on any two elements in the set, we end up with something else, an element in the set. And so that's the first property. The second property is that the operation is associative in that set. So let's say we have plus and we have integers. So z and plus. So basically, uh, if we add any integer to any integer, we get an integer. The operation addition is associative. Then every element has an inverse. So like plus 2's inverse is minus 2. And the last property is that there's an identity, basically an identity to the operation. So like if we add phi and minus phi, we end up at 0. So the that's inverses. But if we add phi to 0, we get phi. So 0 is the identity here. So the same thing, all the properties apply for an elliptic curve. So the points on an elliptic curve form a group. But it's actually an abelian group. Abelian is basically one where the operation is commutative. So in the integers as well, the operation addition is commutative. So the integers and the operation addition also forms an abelian group. This may be quite a bit confusing. So doubts? Any doubts? Please do ask your doubts. Okay, no doubts. Oh, can I not just hear or so, right, we have the points, we have everything. So, another very interesting property is that if we add some point p some point p comma q on an elliptic curve to some point r comma s on an elliptic curve, where p, q, r, s are all rational numbers, then we will end up with a point q1 comma q2, where q1 and q2 are also rational numbers. So that is very nice, very interesting property. So yeah, so how can we actually mathematically compute the addition of 2 points? Basically what we'll do is we'll compute the coordinate equation of the line p plus pq, right? And we'll basically input whatever we get. Like we get y is equal to ax plus b. We'll input it over here. So ax plus b the whole square is equal to x cube plus 17. And we'll just solve the cubic and we'll get x and we'll get y. And we just don't forget to do the reflection. The reflection is very important. So, right. We can do this if we get time. We'll probably not. We'll just do the first two or something. So yes, very fast. So how will we encrypt with this? So like it's already very confusing. How will we encrypt with this? So all ciphers we've done, all the actual ciphers we've done so far were using modular arithmetic. So what we'll basically do is we'll get modular arithmetic into this as well. We'll consider an elliptic curve modulo a prime, which seems very confusing since it's literally a curve. How do we consider this modulo a prime? So basically what we will do is all the points, we'll consider all the rational points at least. So all the rational points on the elliptic curve, we will, since like we'll consider it modulo prime, and since every element modulo a prime has an inverse, we can actually compute p upon q to be p into q inverse. We'll just take that as an integer value. So yeah, so all the rational numbers get mapped to some sort of p cross p square, and the elliptic curve structure basically gets destroyed. We just have random points here and there which correspond to something modulo p. Nice. Actually, not nice, but okay. Fair enough. Sure. So yeah, we now have points on an elliptic curve modulo p. Also note, remember that NP means P added to itself n times. The basis of elliptic curve cryptography now is the elliptic curve discrete logarithm problem. So if we'll remember, the discrete logarithm problem we have discussed was basically that the attacker has to keep multiplying and multiplying and multiplying as long as they don't reach the wanted value, which takes a huge amount of time. This is similar. So basically we have P and C. C is the ciphertext, P is the plain text, and we'll, so what we'll do is we'll keep adding P to, not we, like what Alice does is Alice computes NP modulo P and lets it be the ciphertext. And what the attacker has to do, the attacker has to keep adding P to itself until he or she gets the ciphertext, which is again going to be very troubling for the attacker, just like the discrete logarithm problem. So basically, that's why it's called the elliptic curve discrete logarithm problem. Okay, nice. So the attacker has to check every possible case, and he has to add p to itself on and on and on. And Alice has much faster methods. For example, she can do something like p plus p, 2p, 2p plus 2p, 4p, and so on. So yeah, kind of like that. So okay, so now we'll discuss an actual cipher. This is basically the base of a lot of ciphers, but we'll discuss another cipher, which I like a lot, which depends on this theorem, which is the elliptic curve equivalent of Euler's theorem in number theory in the integers. So what is this? So for any elliptic curve and any prime p, suppose that f is the number of points on the elliptic curve, including p infinity. Note that f is actually finite, right? F is actually finite. So yeah, so f is the number of points on the elliptic curve, including p infinity, and their distinct modulo p. So for any point p on the elliptic curve, what we have is fp is not infinity, it is p infinity modulo p. Note that p infinity is basically equivalent to 1 here. So remember that a to the phi of n is congruent to 1 modulo n. So this is basically the equivalent of that, where f acts as phi of n. F acts as phi of n, which is really interesting, really nice. But this is basically modulo p, where p is a prime. So this is more like Fermat's little theorem, right? So okay, how do we prove this? So this is basically a lot similar to the proof of Euler's theorem, basically the same. So suppose the points are p1, p2, p3 till pf, and consider, since there are p points, since there are f points, right? So now next we'll consider p1 plus p, p2 plus p, and so on till pf plus p. We claim that both of these sets are just the same, but in a different order, basically permuted. Okay, that's fine. So it's basically enough to prove that for pi distinct to pj, pi plus p and pj plus p are distinct. So since basically every point maps to some other point on the elliptic curve, we can suffice to prove that pi plus p and pj plus p are distinct. So in fact, what you can say we can do is subtract p from both sides, but formally we cannot do that, but no one cares about formality, so we'll just cancel this out and we'll get pi is the same as pj, but that's a contradiction. So yeah, so basically this set is equivalent to this set, so their addition is equivalent to this addition. Now we'll ignore the sophisticated theory and formality here again. Cancel P1, P2, PF, and so on. Cancel P1, P2, PF, and so on. And we'll get Fp is congruent to infinity, or the point at infinity modulo P. Very simple proof, basically equivalent to Euler's proof, Euler's theorem proof, which is also like we have elements a1, a2, so on till a5 of n. Multiplying them, we get the same set, just yeah, permuted. So this is very important because this says that the number of multiplications, sorry, the number of additions works modulo f. Sorry, so like if we have n additions like np, then this is basically equivalent to n, whatever n is modulo f into p, right? So this gets a lot smaller since we're considering modulo f, right? So yeah, now we're going to discuss the cipher I was talking about, the 3-pass cipher, which is very nice. So how this works is Alice, Alice, I just draw two lines. Alice picks some secret A. Note that this is not the plain text or the key. This is just A, this is B. Alice picks a secret A, Bob picks a secret B. So Alice has some plain text that she wants to send to Bob. But what Alice will send, since it needs to be encrypted, Alice will send AP or P added to itself A times on the elliptic curve. Like we'll basically represent P at some point on the elliptic curve somehow. Like we can do this individually, but we'll represent it like that. So we'll represent P at some point. We'll add it to itself A times. We'll get AP, and basically Bob receives AP. Bob receives AP. But what can Bob do with AP? Bob knows neither A nor P. So Bob just sadly replies back. What he replies back is B into AP because that's all he has. So yeah, so B into AP. Now Alice has B into AP. The only thing she can possibly do is like either multiply A again, which makes no sense. Why would she possibly do that? So what she does is, since we have F, we have F, which is the equivalent of phi of this, which is the equivalent of phi. We have that, but we don't care. So basically what we'll do is we'll compute the inverse of A modulo P, modulo the prime P that we're considering, and we'll multiply A inverse, like Alice at least will multiply A inverse since Alice only knows A. So we'll get A inverse into B into A B, and basically since it's commutative, sorry, not commutative. Yeah, since we can basically A additions then A B additions then A bar B additions. So this just cancels, and what Alice is basically sending is BP. What Alice is sending is BP. Now Bob has the message. How does Bob has the message? Bob can also compute the inverse of B. Bob can multiply this by B, BP, and Bob gets P. Yay! So basically, we multiply by A, we multiply by B, we multiply by A inverse, we multiply by B inverse. In all of these steps, the attacker cannot get what the meaning of it is because we're not sending the plain text literally anywhere. So, like if we have XP, the attacker will have to add P to itself, it like so many times until he actually gets XP. So, yeah, right. And again, the elliptic curve discrete logarithm problem makes things a lot more difficult for the attacker, which is very nice for us. Any doubts? If there are any doubts, we'll discuss them. If there are not, we can maybe do this, maybe something more interesting. We can discuss RSA, we can discuss this maybe. This is just very, very unsophisticated. Basically, we just input the equation of the line and just do like we just solve the cubic. Not very interesting. So I guess what we can do is something which is actually very like practical. We can do this exercise on the SkyTail cipher. No, as in doubts. Okay. The SkyTail cipher's exercise is this. So this. Remember the factorization thing in the SkyTail cipher. So basically, we'll just count the number of letters, which is GAHOR OTTPE AALNS which is 33 letters in all. And we can basically only arrange this one of two ways, since 1 into 33 and 32 into 1 doesn't really make sense. So we only have 3 into 11, a very big 3 into 11 grid. 3 into 11. Yeah, so I was basically wrong about the six things. It's actually not six things, but yeah, sure. It is though. It is. It is. Never mind. 1, 2, 3, 4, 5. This is a pain. 6, 7, 8, 9, 10. G. Okay, I have to thin this. Oh no. Ah, it's gone. Okay, fine. I can do this without it. Never mind. G A H O R O T T P E A A L N S L S S T T. I just realized I've not been using my mouse to write this, and I just started using my mouse, and it's so more like so much more helpful. E H H EHHSEO TSU. Okay, so okay. Does this actually make sense? GAHALSUNE. Gahalzun. I mean, no, it doesn't really make sense. So we'll have to do this the other way. Oh God. Okay. GAHALN. Okay, wait. GOTPE. Okay. We'll do this the other way. Okay, this is gonna be a pain. I should have just arranged it vertically and read it horizontally, right? I shouldn't have erased the whole data. Okay, wait. I mean, more more like ingeniously, what we can do is G O E E A S. No, 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 not E A. In fact, E L S T H O U. Is it you? Wait, am I doing the whole thing wrong? O T E L. Okay. I cannot do this. E A L L T H E A L L T H E S P. It says got L. No, so it's go TELL. Go tell the SP. Okay, go tell the SPA. Okay, wait. Write this down like this. Go tell. Go tell the SPART ART AN AN ST Spartans. Okay, nice. T H wait T and then H and then O THOU W. Wait, how does this make sense? I must have missed something. A T A N S T H O U W. Go tell the Spartans. Thou. Oh, so this must be thou then. Thou. Go tell the Spartans, thou W H O P P. Is it W H O P? H O P A S S A S S E S E S E S T B Y T B T B Y. Okay, after hours of long effort, which could have been reduced by a computer to like a very short time, but okay. So we basically get go tell the Spartans, go tell the Spartans thou who passest by. Go tell the Spartans you who passes by. Okay. Are there any doubts at the end of the session? Mm-hmm. Okay, yeah. So I guess we can end the session here. Hope you liked it. And I'm very disappointed I couldn't get to discuss Fermat's last theorem. Okay, yeah. So I will stop sharing.
Thanks for the class. Should I stop the recording?
Yeah.
Okay.